Recently, due to the improvements in computer performance, real-time simulation of VR world have been made possible. Along with it, the demand of the VR simulation such as Suguri simulation and assembly simulation is increasing. These simulation require the movements such as slight motion of fingers and complex movements of hands, like rotation or twisting. In Sato Laboratory, we focused on responsiveness of force, and we have developed wire-driven haptic interface. The property of wire is light and have tolerant to tension. It gives high rigidity and fine responsiveness to output force instantly. This is a two-handed multi-finger haptic interface, and we can manipulate VR objects by our own 8 fingers without little finger. But this device is weak in large change of hand posture, because the wire interference will occur due to fixed frame. This is a one-handed multi-finger haptic interface, and we can use all fingers of one hand. But if we prepare 2 of this device, it is difficult to use by 2 hand, because of the direction of the frame rotation. In this study, we develop a two-handed multi-finger haptic interface with rotary frame to manipulate VR objects by our both hands and all fingers, and rotate the frame optimally to reduce the interference of wires. This is a two-handed multi-finger haptic interface, SPIDAR-10. We can use all fingers of both hands, and we can pick and grasp VR objects. And SPIDAR-10 has 2 cylindrical rotary frame, and they can rotate one axis direction like this. So, user can rotate or twist their hands. The frames rotated correspondingly to the movements of hands. And both frames rotate definitely. Furthermore, frame rotation prevent the interference of wires. The frames are rotating by using proposed method. When the finger approaches to the home position, it is ideal condition for SPIDAR system. It means to reduce the length of tensioned wire. It provides 3 advantages, so we aim to rotate frames to minimize the total length of wires. This figure shows the case when we put only one finger to the SPIDAR-10, and we assume the current frame angle as theta. First, the finger moves. It changes the length of tensioned wires. So, we will evaluate the frame angle to minimize the total length of wires. We assume small angle as d and calculate the sums of wire length when we virtually rotate the frame by theta minus d and theta plus d. We choose the objective angle which minimize the total length of wires from them and execute frame rotation. By using proposed frame rotation control method, we can suppress the elongation of wire. And it provides fine operability and accurate finger position estimation. User can operate such a difficult work comfortably. To realize the operating environment close to a real world, we introduce hand shape estimation into this system. This system will improve users' recognition of the relations of fingers by simulating the hand in VR world. We will build the operating environment that is more comfortable than a conventional system. In this research, we propose two-handed multi-finger haptic interface with rotary frame. Proposed the frame rotation control method which focused on the total length of wires. And we proposed hand shape estimation into this system.